Okay, the next talk is producing shorter congruence closure proofs in a state-of-the-art SMT solver. And the talk is given by Bruno Andreotti.
Right, thank you. So equality reasoning is a very essential part of modern SMT solvers. It's, of course, useful for the theory of equality and uninterpreted functions, but it's also heavily used internally in other theories. And this is usually done using what we call a congruence closure algorithm, which allows the solver to determine equivalences between different terms. So for SMT solvers, however, it's usually not sufficient to just say whether two terms are equivalent. So we might also be interested in an explanation of why they are equivalent. So for our cases, an explanation here is just a minimal subset of the input literals that is sufficient to make the terms equivalent. So you might want this, for instance, if you have a proof-producing SMT solver. So if you're making a proof for the entire problem, a part of that proof is going to be equality reasoning, so you need an explanation for that. But also these explanations are used for conflict clauses in the SAT solver, which kind of guides the search through the problem. And ideally, of course, we want these explanations to be small, right? So if you are producing a proof in the end, then a small explanation will result in a smaller proof, which is easier to check and reason about and all that. And also, the explanations, when they are used as conflict clauses, well, a small conflict clause will prune a larger part of the search space. So that can actually speed up the search of the solver as a whole, which is quite interesting. However, we have a theoretical result that shows that finding the minimum explanation for a given congruence closure problem is NP hard. But nonetheless, we can try. And a few years ago at VMCAI', Oliver Flatt and collaborators, they presented a new algorithm for congruence closure, which can demonstrably produce shorter explanations. And their work was in the context of an equality saturation tool, which is called the EG. And while that is very interesting and complicated on its own, we are interested here in SMT solvers. And they offer a few different challenges from equality saturation. So for one, we have backtracking. So the solver can assert a few equalities and then go back, so we have to deal with that. And we also have to interact with different parts of the reasoning of the solver, right? Different theories or the SAT solver as a whole, things like that. So the main contributions of our work here, so we modified the Oliver Flatt's greedy algorithm to work in the CDCLT algorithm that is used in SMT solvers. We implemented this approach in CVC5, which is a modern, industry standard, not standard, but like industry strength SMT solver. And we also did a quite extensive experimental evaluation to see if this implementation is worth it or not. So more formally, we can say that the property of congruence states that if you have two sets of terms and we have a function, an arbitrary function applied to those terms, we say that the function applications are equal if the arguments are pairwise equal. So more concretely, if you have, for instance, if A equals B, we can derive that f of A equals f of B for any arbitrary function f. Additionally, we can define that for a given set of equalities, we say that their congruence closure is the minimal equivalence relation that satisfies these equalities and is also closed under this congruence property. Traditional algorithms for finding congruence closure, they are based on a union find data structure, and they construct a graph which we call the equality graph, or the E graph, which represents the equivalence relation that we're going to be building. And once we have that graph, finding an explanation amounts to simply finding a path between the two terms in the graph. So let's, and looking more detailedly at this graph, so each term in the problem will become a node in the graph. And the graph is going to have two types of edges. The equality edges, they correspond directly to the input equalities given to the congruence closure. And we're also going to have congruence edges, which they represent an equivalence that we derived via congruence. So a congruence edge, it's going to have what we call a justification. So the justification for a congruence edge between two function applications is going to be the set of pairs of terms that are the arguments of this application. So in a sense, the justification is like the pairs of terms that have to be equivalent in order for the edge to be valid. So let's look at an example here. So we have a bunch of terms, and we're going to be adding equalities to the graph and seeing how we can construct this E-graph. So for instance, if we add the equality x equals y, we're going to add here an equality edge between x and y, which we're denoting with a simple line. But we're also going to add a congruence edge between g of x and g of y, which is this double line here. And here we're going to say that the justification of this congruence edge is the terms x and y. So we can continue. Let's say we add y equals z, which adds another equality edge. So when we add, for instance, z equals w, now we know that the terms x and w are equivalent. So we can also add this other congruence edge between f of x and f of w. So let's say we add the equality x equals z. So this equality is in some sense useless to us because we already know that x and z are in the same equivalence class. So we just ignore it and continue. And we go on like this. So v equals u of y, f of w equals u of x, blah, blah, blah. And let's say at the end, OK, so here we have another useless equality, right? F of w equals v. So we already know that v and f of w are in the same equivalence class. So again, we ignore it. And let's say at the end, we add u equals f of x, which causes the congruence edge between f of u and f of v to be added. So let's say we want the explanation for the equivalence between f of u and f of v. How would that work? So like I said, we first find the path between them in the graph, which is going to be just this edge. There's an edge between them. However, since this is a congruence edge, we also need its justification to be valid. So we also have to find an explanation for each pair of terms in the justification of this edge. In this case, the justification is just the terms u and v. So we have to find a path between u and v, which is quite simple. It's this one. But now, again, we have two more congruence edges that we need to explain. So we, again, recursively explain the justification of these edges. So let's say we start from this edge here on the right. We have to explain that x equals y, which is just this path here. And then for the other congruence edge we missed, we have to explain that x equals w, which is going to be this. So at the end, we have this E graph. And the explanation was for the equivalence between f of u and f of v was just the entire graph, right? So every equality that we added to the graph was needed to explain this equivalence. Right. So you might have noticed that we discarded some of the equalities that were between terms that we already knew were equivalent. And that was not an accident, right? So you might think that we can use these equalities to allow us to find a shortcut in the graph, or allow us to find a shorter explanation between two terms, and thus a shorter proof. And that's exactly what Flatt's greedy algorithm tries to do. So it makes use of these redundant equalities to find these shortcuts in the graph. So let's go over again the example. So everything starts the same, so x of y, blah, blah, blah. But once we have this z x equals z equality, which was redundant, we don't discard it. So we add it to the graph using this dashed line here, which represents a redundant edge. So we continue. Later on, we have another redundant edge here between f of w and v, which we add again, and so on. And then at the end, we're trying to find the explanation for f of u and f of v. So it starts out the same. We find a path between them. However, now, when we want to explain the equivalence between u and v, well, we have two paths to choose from. So we have a little bit more freedom here. So let's choose the new path, right? The one that uses the redundant edge. And now, as you see, there's only one congruence edge in this path, which we need to explain as well, which is between x and w. And again, we have two different paths between x and w, so we can choose. So let's again choose the new one. And this is the final explanation for the equivalence between f of u and f of v. So as you see, this is quite a bit smaller than the previous explanation. So keeping these redundant edges allows us to find these shortcuts and get a smaller explanation, at least in theory. However, one thing you might have noticed is that now that we have these redundant equalities, the graph for each equivalence class is no longer a tree. So it can be just a graph in general. Which means that while before there was a unique path between any two terms in the graph, now there can be multiple paths. So how can we select which path to use to find an explanation? So that's exactly what the greedy algorithm tries to do. So it does that by first assigning a weight to each congruence edge. And we see how these weights are calculated. But they are defined to be the size of the explanation for their edge, or at least an estimate for the size of the explanation for that edge, as is returned by the traditional congruence closure algorithm, which is without using redundant edges. So basically, we call the old traditional algorithm for every congruence edge to find an estimate for its size and use that as the weight. And then, so here's the algorithm for doing that, right? So it's very simple. So at the start, the weights is infinite for everything. But for every edge, which is a congruence edge, we call the classical explanation here and get its size. And for equality edges, the weight is just 1. Right. So once we have the weights computed for the graph, to explain the equivalence of two terms, we just find the shortest path between them using those estimates as weights. And of course, again, we're going to recurse on congruence edges every time we find them. However, there's a little added caveat here, is that we don't do this recursion forever. So we only go into a certain depth, which is determined by a fuel parameter, and we'll see how this works a little bit in the pseudocode. Right. So here the first thing is, so when the fuel is 0, so if you have ran out of fuel, we are going to use the classical explanation again. So the reason for this fuel thing is because this explanation algorithm is slower than the traditional algorithm and has a worse complexity. And in order to keep things more efficient, we have this fuel which basically uses the algorithm only up to a certain depth. And then if the explanation is too deep, we just give up and just use the classical algorithm, which has a better complexity. But in the general case, what we do is we find the shortest path between the two terms. This just using Dijkstra algorithm or something. And then for every edge in that path, if it's just an equality edge, we add it to the explanation. But if it's a congruence edge, we go through its justification and explain everything recursively. Of course, decrementing the fuel. Right. So the way I described it until now, this algorithm kind of depends on the input having enough redundant equalities so we can find shorter paths and can actually have an improvement in the explanation size. So that's not ideal. So on top of that, we also compute extra redundant edges to kind of maximize our chances of getting a shortcut in the graph. And the way this is done is we find terms that are in the same equivalence class that have the same canonical form. So the canonical form of a term is defined as if you have a function application, you're going to take each of the arguments and you're going to take the representative of the equivalence class of that argument and you're going to apply a function to that. So in a sense, the canonical form of a term, should I say, if two terms have the same canonical form, it means that they are directly equal because of congruence. So we can add a congruence edge between them. Here is the code for computing these extra edges. So we keep a data structure which maps a congruence form term, a canonical form term, into a set of terms that has that as their canonical form. And for every term in the equivalence class, we find every other term which has that, the same canonical form, and we add an edge. However, do notice that we only do this up to a limit. And the reason for that is because this algorithm, in theory, it might add edges, a quadratic number of congruence edges in relation to the input problem, which is very bad for performance. So we only do this up to a limit. Right, I mentioned, talk a little bit about this later, but this limit is usually a linear multiple of the number of total edges. So we keep the number of edges in the graph linear with regards to the number of nodes. Right, so this algorithm, as described, works great for the application it was developed for, which is EGG, this equality saturation tool. However, when we are adapting this algorithm to an SMT solver, there are quite a few interesting, or should I say annoying challenges, right? So for instance, okay, I thought I had it on the slide, whatever. But so I'm gonna go over quickly some of the challenges that we had, but there were many, so I'll try to be quick. But the first one was dealing with backtracking. So as you know, SMT solvers, they try partial solutions, and when they determine that one solution is invalid, they have to backtrack to a previous state. So our algorithm has to be able to efficiently revert the state back to a previous point. So the way we do this is, well, the first thing we have to do is that we have to lazily compute the weights for the greedy algorithm, so we don't do extra work that we are not going to need. But also when we backtrack, we have to clear the computed weights that have become invalid. So we have to safely determine which weights are invalid and which weights we can keep when we're backtracking, which is a bit tricky. So another annoying thing is the limitation on the number of congruence edges. So by default, the greedy algorithm limits the number of edges such that at any point in the graph, the total number of congruence edges is less than half of all edges. However, this is not enough for SMT solvers, because an issue we had, for instance, is when at a certain point the solver adds an equality and then creates a bunch of congruence edges and then backtracks and then adds another equality and then creates a bunch of edges and backtracks again. So in a sense, we're kind of doing a lot of work and adding a lot of edges that we're not going to use. So what we had to do is to limit the total number of edges which are added kind of historically throughout the whole run of the solver and not just at any point in the graph, which is a bit more complicated. But in general, like the biggest challenge we had was dealing with the implicit dependencies that the eGraph has with other parts of the SMT solver. So when we were discarding the redundant equalities, we could never have any circular proof in the solver. And that is because once we add a congruence edge, the path between the terms in its justification is fixed in place. It can never change. However, this is no longer true because we can add a redundant edge afterwards in that path and add a shortcut. But this can create a problem when the congruence closure engine is interacting with other parts of the solver. So for example, let's say the set solver asserts a bunch of equalities into the congruence closure, A equals B, C equals D, and B equals C. So at that point, we can derive by congruence that f of A equals f of D. So the congruence closure engine is going to do that, and it's going to return that information into the set solver. So let's say then that the set solver, for whatever reason, maybe it has a clause that does this, or maybe there was some theory reasoning that does this, but let's say it derives A equals D based on this f of A equals f of D equality. So it's going to derive that, it's going to send that to the congruence closure engine because it is an equality. And at this point, we're going to add that as a redundant edge, right? Because we didn't have this equality before, but we already knew that these two terms are equal. So what happens now when the set solver asks the congruence closure engine for an explanation of f of A equivalent to f of d. So if you think about the E-graph that we would have constructed in this situation, it would look something like this. So here on the bottom, we have the three asserted equalities. And on the top, we have the congruence edge that we added. And the dashed line here is the redundant edge that was added later. So when explaining f of a equals f of d, it would be very tempting for the algorithm, and it's probably what it's going to do. It's going to find the path between a and d that uses the redundant edge directly, because that's probably shorter than the other three edges. However, if it did that, what's happening is that the set solver derived the a equals d equality based on the f of a equals f of d equality that the congruence closure gave it, while the congruence closure engine is now saying that the f of a equals f of d equality is explained directly by the a equals d equality. So we have, in a sense, a circular proof, right? So the two parts of the solver are saying that one thing depends on the other in a different way. So that's a very tricky problem to solve, and we tried many different solutions to address this. But at the end, the solution we found that was simpler and easy to implement and that actually could solve this problem was what we call the level system. So we have augmented the equality graph to add an edge level to each edge in the graph. And in this case, this edge is just the number of edges that exist. This level is just the number of edges that existed in the graph prior to that edge being added. So in a sense, it's just like an incremental counter. So each edge is numbered. And when we're explaining a congruence between two terms, we can only use edges which were added before these two terms were known to be equal. So for example, let's say we have this, so this is the previous E-graph, but now we have the edge levels added. So as you can see, so the first three equalities have level 0, 1, and 2 in the order they were added. And then the congruence edge has level 3 because we discovered that it was equal after that. But now the redundant edge has level 4. So when we are explaining the congruence edge between f of a and f of d, we cannot use the redundant edge because it has level 4, which is greater than the level of the equivalence. So this approach fixes perfectly the correctness of issue that we had before. However, it is also quite restrictive in how we can use redundant edges in the proof. So, this is a problem, as we see in the evaluation section, but we think that maybe a different architecture of the set solver can maybe allow more flexible solutions, because this is kind of like deeply linked into how the set solver keeps the asserted literals. So let's follow on to the evaluation, right? So to evaluate this implementation, we ran on a very large set of problems from SMT-LIB. And we were focused on the theories of EUF, of course, because it involves a lot of equality, but also on the theories of strings and arrays, because they are big, complicated theories that also use equality reasoning internally. And also the theory of linear arithmetic, mostly because if you're going to use arrays, you're going to need linear arithmetic usually. So we split the analysis into basically these three groups. So we have the theories which are based on arrays, based on strings, and all of the remaining logics. And we focus our evaluation on just the impact of that greedy had compared to the traditional algorithm as it was implemented in CVC5, which we refer to as vanilla. So this is a summary of our results. So as you can see, the impact on runtime is quite significant, and there are many reasons for that. So we are increasing the number of edges, which kind of increases the graph as a whole. Also, the path finding algorithm is much slower than just finding the unique path between two terms in a tree. However, that runtime comes at the benefit, at least, of having a smaller proof. So we were able to find a very consistent reduction in proof size of about 3%, which is not very impressive, but you have to understand that this proof size is the proof at the end of the solver. So it's going to involve other types of reasoning, it's going to involve other theories, and also it might not include all of the explanations that we computed. So we also measured the local explanation size. So for every call to get explanation, we measured the size of the explanation returned and added all that up. And as you can see, this is very theory dependent, right? So for the logics which don't have either arrays or theory or strings, the reduction was quite big, more than 20%. But for strings, for instance, it was less than 1%. So as you can see, these theories use congruence closure engines in very different ways. But on average, we had around an 8% reduction in the local explanation size, which is quite a positive result in our opinion. So this is a scatter plot of the runtime separated by each of these theory groups. And what's interesting here, so you can see that in general, there are more dots above the line. So the axis here, so on the x-axis, we have the runtime for vanilla in milliseconds. And on the y-axis, we have the runtime for greedy. And the 10 here is because we're using a fuel value of 10. So we also tested out different fuel values, but they didn't make much of a difference. So as you can see from all of the three theory groups, we have more dots above the line, which means that greedy was slower, especially for very large benchmarks. So for instance, for strings, you can see that there's certainly some degenerate behavior here, where the very large benchmarks, they take quite a long while to solve in greedy. But the interesting thing is that there are a few benchmarks which are faster to solve in greedy. Especially for the arrays theory, there is this weird cluster of benchmarks which took a few seconds to solve using the traditional vanilla algorithm, but took only a few milliseconds to solve using greedy, which is quite an interesting result, right? And the reason we think this is happening is because, like I said in the beginning, smaller explanations can result in a smaller conflict clause given to the SAT solver, which in turn can speed up the SAT search. And apparently in some cases, especially for the arrays theory, that can make quite a big difference. So additionally, we also measured how heavily the redundant edges we added are actually used in explanations. This is kind of to infer how the level system is restricting this. And we saw that for all of the returned explanations, the average number of redundant literals in the explanation is 3.5%, which is not a lot, especially considering that, so it's also heavily theory dependent as well. So like I said, strings, it sucks for some reason. But this is not a lot, especially considering that on average for the whole Lie graph, around 40% of the edges were redundant. So this really indicates that the level system, while it is necessary to fix the correctness issue, it does include some problems in being too restrictive with which edges are used. So in conclusion, I hope I was able to convince you that this kind of approach that uses redundant edges has promise to be efficient in an SMT solver. So while these techniques, they have a quite measurable impact on the explanation and proof size, they do come at a significant increase in runtime, though sometimes it can also improve runtime for some exceptions. And another interesting conclusion is that despite having many redundant edges in the graph, they're not heavily used in the returned explanations. So for future work, we really want to try as a priority to improve the runtime performance of this. So this can be done just by better optimization of the implementation, which are sure there's a lot of work to do there, but also smarter heuristics on how we search for a path in the graph. We also want to develop new heuristics for computing the edge weights. So one interesting idea, for instance, is to take into account the SAT level of the edge literal. So for instance, if you have a literal which was asserted at a very old level in the SAT solver, it might be interesting to have a lower weight to prioritize using that literal in the explanation, because that literal will correspond to a larger section of the search space, and you can speed up SAT search even more. We also want to explore how we might address the implicit dependencies issue beyond the level system. So like I mentioned briefly, this level system is kind of deeply related to the way that the SAT solver stores the literals in the trail. So we don't think that there is a current alternative solution that would work with the way that SAT solvers currently work in CVC5. However, there is some interesting work, for instance, in like chronological backtracking SAT solvers and things like that, where the trail is a little bit different. And in that case, we might be able to use a more efficient system and make better use of the redundant edges we have. But yeah, thank you.
Thank you very much. Time for questions. David?
This may be a very naive question. So for
Yeah.
SAT solving, so what some people do is they do not try to optimize the proof that is produced by the SAT solver.
Right.
And then they use a tool that optimizes the output before trying to replay the proof in like in a proof assistant where loading a large proof is really expensive. Have you thought about post-processing?
That's an interesting question. So there is a quite a robust system for this in SMT on CVC5 at least, which is it's called like proof elaboration. So before you print out the proof, you do this elaboration section. I have not thought about using this for this tool. I'm not sure how we could be able to efficiently track like the redundant edges. So maybe we just compute them afterwards. I don't know. It's not a path that I explore, but it seems an interesting future work.
Hey, thanks for the great talk. I was wondering, I guess this might have been exactly what you've kind of mentioned in the future works, like, even though I wasn't exactly sure. So previously you've mentioned that congruence edges, you kind of weigh how costly they are by kind of going back, and if you take this congruence edge, then you would also have to take these other paths to kind of associate the cost of them, because you know that, well, they cost more than what they depend on. I was wondering for the SAT stuff, if you just get A equals D, that also sounds like a dependency on the prior path, and if you use kind of the same idea of computing the cost of that the same way, then it sounds like it can't use that edge because it would be more costly.
So that is true. So that was one of the many approaches we tried for preventing the problem. So there are two ways of doing this. So you can either record how the term was derived in the stat solver, and it kind of like what we called provenance when we were trying this, which is like which literals were depended on by this literal. And in that case, it's going to be equivalent to the level system because the weight is going to be monotonically increasing because, again, it's going to match exactly with the trail of the stat solver. Another approach you can do is kind of analyze the literal afterwards and try to infer the provenance from that. And we tried that, and in theory, it could work. So we didn't produce any proof which was invalid, but the proofs are still rejected by the stat solver because the stat solver expects that the specific trail it has, which is, I guess, like a topological ordering of the implication graph, it expects that that specific topological ordering is respected, which is one of the things that might change if you have a different architecture for the stat solver. Does that make sense?
Yeah, I think let's chat afterwards.
Yes,
I think it might depend on more SMTs that I just don't know.
Yeah, cool.
Thanks.
Okay. Other questions? Okay, I do have a quick question for you. Can you go back to your slide? I think it was 32. Yeah. So the final, this is the reduction in the final proof size, right?
Yeah.
In the middle column. I assume this is the average over that 160,000 benchmarks. But what is the standard variation? Because in some of them you may gain a lot, in some of them you may not gain anything.
So
what I'm saying is average may actually not be a good representation.
Yeah.
You might be doing much better than this in the majority of them.
Yeah, that's a good question. So we did include the scatter plots similar to this one in the paper. I didn't include here because they're kind of boring, right? But the general idea is that it's very close to the diagonal. So there's not a lot of variation as there is in the runtime. It's mostly consistent.
I see. So the average is a good representation.
Yes, in this case it is.
Right, fair enough. Okay, any final questions? No. Okay, let's thank the speaker again.
Thank you.